Let's do the third free response question on the 2004 E&M test. So let's read the problem. So we have a rectangular loop. It's 3L and 4L, lies in the plane of the page as shown above. A long straight wire also in the plane of the page carries a current I. Calculate the magnetic flux through the rectangular loop in terms of I, L, and fundamental constants. Okay, so, this looks like we need to use a little bit of calculus, doesn't it? Magnetic flux, well, let's write the symbol for it, is equal to B dot dA. Now notice I didn't put a closed surface on here because this is not a closed surface. Here's a surface right here. Grab the wire, you've got flux, magnetic flux coming out of the page. But here's the problem. As you move away from the wire, the flux density, or the magnetic field, becomes weaker. Because we have this, we're going to say that B, well, let's do it under here. B is equal to mu naught I over 2 pi r, where r is the distance away from the wire. And that's a long straight wire, and that should be on the equation list. Let's see. Oh, it's not. Yeah, it's not on there, is it? Well, that stinks. So you need to know this right here, long straight wire. You need to memorize that. That's a very, very common one that you need to know. And then you can derive it fairly quickly from Ampere's law, but that's a little bit time consuming. So B is going to be equal to mu naught I over 2 pi r, but r varies. So what we need is a differential area that's in terms of r. Well, here's what I'm going to do. I'm going to draw a little differential area here. And it's going to have a thickness of dr, and it has a width of 4L. So 4L times dr gives me a little area. Okay? Now I need to decide how r varies. Well, r is going to go from L, look, here's L, and then you have 3L additional, so that's a total of 4L away from the thing. Let me zoom in. Okay, so, and this is something we can integrate. Let's clean it up a little bit though. The 4 cancels the 2, so that leaves 2 mu naught I L over pi times the integral of dr over r from L to 4L. Now you're all in Calc AB or Calc BC. This is a very doable integral. So the magnetic flux is going to be equal to 2 mu naught I L over pi times the natural log of r evaluated from L to 4L. So that's going to be 2 mu naught I L over pi. And then what's the natural log of, that's going to be the natural log of 4, right? Because this is going to be the natural log of 4L over L. So the L's cancel. It has to cancel because this has to be dimensionless. This is just plain old 4. And that's my answer. I think. Let me check the answer key. Oh, that's next. Okay, let's see. Yay, clapping. Yep. All right, so that's right. That's really, really hard for part A. Sometimes part A's are killer. Sometimes they're trivial. But don't assume that, look, I imagine most of you got stuck on part A. All right. Does that mean you can't do part B? No. You can do part B. And you can get part of this. Look, if you remember to write this down, you're going to get a point. And then maybe you try to set it up with some kind of area or whatever, and you're going to mess it up. But we live by partial credit here. Partial credit. Show them what you know. If you get stuck, that's perfectly normal to get stuck on these problems. Okay, let's do part B. Okay, so it says starting at time t equals 0, the current in the long straight wire is given as a function of time t by this. The current in the loop is in which direction? Justify your answer. So it looks like the current, I'm going to draw a quick sketch of the current. When t is 0, we're at our maximum. So we have exponential decline of the current. So the current is getting less and less. So the induced current in this loop, let me zoom out so you can see that. This has got flux coming out of the paper. Now that flux is going to start disappearing as the current in the wire gets less and less. That's going to induce a current in the loop that will try to keep the flux the way it was. It will oppose the rate of change of flux. So since we're getting less and less flux coming out of the paper, it will induce a current to try to create flux out of the paper. So therefore, the induced current will be counterclockwise. Justify your answer. Lenz's law. And then I'd write as current diminishes the induced current, creates flux out of the paper. I don't know, something like that. Just write some stuff down. Let them know you know what Lenz's law is. Here's what they wrote in the solution document. It says, the decrease in current means a magnetic field which points out of the plane of the page is decreasing in magnitude. Using Lenz's law, the induced current thus needs to create a field to counteract this change. The current must therefore be counterclockwise to create a field directed out of the page. Okay. So So if all you do is say Lenz's law or the right-hand rule, you'll get 1 out of 2 points. So if you're running out of time, you don't want to spend 10 minutes writing an essay here. If you just say Lenz's law, you're going to get a point. You need to describe it a little more clearly in depth to get the 2 points. Because look, you get 1 point for saying counterclockwise, and you get the 2 points for explaining why. If you say because of Lenz's law, you get 1 out of those 2 points. Maybe that's good enough because explaining all this might cost you more points because you're running out of time. So you might want to save your explanation for later and go back to it. All right. Oh, great, there's more. The loop has a resistance R. Calculate each of the following in terms of R, I naught, K, L, and fundamental constants. Okay, the current in the loop is a function of time, T. Well, this is going to be Faraday's law. Whenever you're dealing with induced currents, you're dealing with Faraday's law. So Faraday's law says that the induced current is, or in EMF, I'm sorry, the induced EMF in the loop is going to be dp dt. Now, this phi is going to be equal to, well, we had 2, here are the constants, 2 mu naught L natural log of 4 over pi. And then, because that's all constant, and then it's just going to be di dt. Now, what if you screwed up all these constants right here? Stay awake and pay attention. If you screwed up these constants, look, you can still get lots of points for this. Say, I don't know what these constants are. I couldn't do part A, but I know it's a function of the current. So I'm going to just call this, like, you can just call this A, like capital A, a big constant, big collection of constants, and times di dt. And so, well, what is the ID? So the induced EMF is going to be A times d dt of, and what did they give us? For the current, it's I naught times e to the negative t over, or they have, oh, negative kt. So we're going to take the derivative of that. So that's going to be A, I naught. And then what is the derivative of e to the negative kt? We'll use a chain rule. You got negative k. And then just e to the negative kt. That's the derivative of it. Now notice this is kind of nice. I defined all this junk out here to be A, so I don't have to copy it down over and over again. But I don't want the induced EMF, I want the induced current. So E equals IR. So I, the induced current, and this is different than this I. This is the I in the wire. This is the I in the loop that gets induced, is equal to E over R. So that's going to be all of this stuff over R. So I'll just go ahead and go 2 mu naught L natural log of 4 over pi. Okay, that's A. And then we have to divide by R. And then we have to multiply by I I naught, and then we have a negative k times e to the negative kt. I believe that's all. Oops. Messy problem. Look at all those constants. Let's check my work here. Let's see, 2 mu naught I naught L K pi over r e to the natural log of 4 e to the, yeah, I got it all. Now I have a negative sign that I carried in there, but the negative just indicates that it's going to be in a direction that will create magnetic flux to oppose the rate of change. So we don't really need to keep that negative. Now part D, the total energy dissipated from t equals 0 to infinity. Well, here's what and this is a trick that, and by the way, if the bell rings, just let me finish. Power equals the time rate of energy. So the change in energy is equal to power times time, if I want the total. Well, delta U is equal to the power. Well, that's I squared R. That's my power time, taking the integral of time. You're going to go from 0 to infinity. Well, you're going to take all this and square it. Now I'm going to call all this crap here, I'm going to call this B. So it's going to be B squared R, and then you have to square this, e to the negative 2 kt dt from 0 to infinity. This is a ridiculous problem. So B squared R times integral from 0 to infinity Now I think you have 1 over a, right? Here's a, and I believe that the integral of that, and I think they give you an integral table on your equation list that lets you do that. Oh, they don't have the a in there. That's kind of crappy. All right. But you have b squared r over a, which is negative 2k, times e to the negative 2 kt, evaluated from 0 to infinity. Well, when this goes to infinity, it's 0. When it's 0, this is 1. So it's going to be b squared r over 2k. So you take all of this, square it, multiply it by r, divide it by 2k, and I think that should be the right answer, and the bell's about to ring. What? Oh, I'm off screen. I'm sorry. Thank you. So that's the fast way to do it. Hey, before the bell rings, let me just say this. When they ask for the energy out of something or whatever, remember it's almost always this technique, power times time. If you multiply power times time, you'll get total energy, and then you integrate. All right, that's as far as I can go. That is all.